Let's turn now to looking at examples of limits at infinity. So we're talking about finding limits of a given expression as the variable either approaches positive infinity or negative infinity. And there is a very specific way in which we tackle these, different from the problems in which we were doing a limit as the variable approached a number. Very different strategy. So in this case, we have the limit as x approaches infinity of 3x minus 2 over x plus 4. Once again, you could easily graph this on your graphing calculator, and what we're really talking about is what we refer to in mathematics as the end behavior of the graph. If you were to look at the far right extremes of this graph, what is happening to the y value as your x's get bigger and bigger and bigger? So the way in which you approach these algebraically is we're going to divide through by the largest power of the variable. Now, if you take a look at what we have, the largest power of the variable overall is just x to the first. So we're going to divide everything by x to the first. So 3x over x minus 2 over x, and then big denominator, x over x and 4 over x. Essentially, in doing that, you're dividing by 1 because everything is getting divided by the same thing. So that's the idea, the theory behind it. So now you just simplify what you can. So obviously these x's cancel, these x's cancel. Just don't forget that's a 1 there now. Okay? So let me just rewrite what we have at this point to make it a little bit easier. So we have 3 minus 2 over x. And then remember, this was a 1 plus 4 over x. All right, let's talk about these little fractions. Now think about what's going to happen to those as x gets bigger and bigger. So think about if we had the fraction 2 over 10, 2 over 100, 2 over 1,000, 2 over 10,000. Notice how that fraction keeps getting smaller and smaller and smaller? And eventually, if we had maybe 2 over a million or 2 over a billion, that fraction is really, 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 really small. And it's essentially getting closer and closer to 0. So what we say is that zeroes out as x is going to get infinitely larger. And notice the same is going to happen in the denominator with 4 over x. So notice what you're left with is simply 3. 3 over 1, and that's your answer. So if you were to graph this, and you can try this on your graphing calculator, graph the original function 3x minus 2 over x plus 4, what you should notice as you look at the far right extremes of the graph is that your graph, your curve, essentially is leveling off at a y value of 3. Because remember what a limit is. A limit is a y value that you get closer and closer to. You may or may not hit it. This is a case in which you're getting closer and closer to 3. Chances are you're not going to hit it. You're going to have a horizontal asymptote at y equals 3. So give it a try in your graph and see that that's really what happens. So in the meantime, let's take a look at another problem. So I thought I'd change it up and go with n's instead of x's. But same strategy. Since we're doing the limit as n approaches infinity, we're going to divide through by the largest power of the variable. So in this case, that's n squared. So everything gets divided by n squared. Notice as we're doing these, we're keeping our limit notation until the very end. Remember our overall guideline, so long as we still have that specific variable in question in the problem, we are keeping our limit notation. So let's just start simplifying what we can. So that simplifies to 1. This simplifies to like 1 over n. Okay, and 1 over n squared we can't do anything to. So let's just rewrite what we have. So we have 1 in the numerator, we have 1 over n here, and 1 over n squared here. So think again what happens to those little fractions in the denominator. So think again, as n gets bigger and bigger and bigger, each of those fractions gets smaller and smaller and smaller, essentially zeroing out. So what you really have is 1 over 0, which we know that tells us the limit's not going to exist. But once again, we could figure out, well, it might not exist, but is the y getting bigger and bigger and bigger, or is it getting smaller and smaller and smaller? So the way we figure that out is go back to your original and imagine putting in a really, really, really big number in place of n. And think about what kind of answer you would get out of that. And obviously in this case we're going to get a positive answer. So what that tells us is that this limit doesn't exist, but it approaches positive infinity. And again, you could graph it on your calculator, and you'll notice at the far right extremes of the graph, your curve just keeps going up and up and up and up and up. So let's take a look at one more. So same strategy. Think about what it is we're going to divide through by while I get this set up. So the largest power of the variable in this case is x cubed. So everything is getting divided by x cubed. So we start simplifying. So these cancel out. Don't forget you're left with 2. Can't do much to 5 over x cubed. Now you can start combining steps if you'd like, because we know 5 over x cubed, remember, as x gets bigger and bigger, that's just going to approach 0. Same thing's going to happen here. To the other one, let's see what happens there. This cancels, but we still have an x down below, so we're left with 3 over x, and what's going to happen to that? That's essentially going to zero out as well. So this is another one. Really all we have is 2 over 0. So that tells us that this limit does not exist. But once again, we should be able to figure out if it tends towards either positive infinity or negative infinity. So again, go back to the original. Think about what kind of answer you would come out with if you were to substitute a really big number in place of your x, and you would come out overall with a positive answer. So we say this limit doesn't exist, but it approaches positive infinity.